Hello friends, I am Dr. Dinesh Kumar Mishra, Professor Pharmaceutics, College of Pharmacy, IPS Academy, Indore. So I am back with another episode of parental products. In earlier episodes, we have learned basics of parental products, routes of administrations, vehicles, formulation details and selection of containers and closures. Here, have a look on highlights of current episode. Cleaning of containers and closures, preparation of solution in suspension, filling procedures, sealing or closing of ampoules, vials, etc. So friends, let's begin our today's episode. We'll start with module 1, that is cleaning of containers and closures. It's a pre-filling treatment. Before filling of the preparation, we go for cleaning of containers. Containers as well as equipments in parental products must be thoroughly cleaned. Even fresh unused container may be contaminated with debris like dust, fibers, chemical films and other materials arising from sources like atmosphere, cartons, the manufacturing process and human hands. Residues from earlier use must be eliminated before reuse. A variety of equipments are available for cleaning of new containers for parenteral preparations. These vary in complexity from a small hand-loaded rotary rinser to large automatic washers capable of processing several thousand containers per hour. The selection of the particular type will be determined largely by the physical type of containers, the type of contamination and the number to be processed in a specified period of time. It is the responsibility of manufacturers to ascertain scientifically justified acceptance criteria for cleaning validation. Cleaning is accomplished mainly with high pressure rinsing treatments delivered automatically within the equipment, and it is generally followed by steam sanitization through the same system. The glassware or metalware is automatically conveyed, usually in an inverted position, through a series of rigorous high pressure treatments including hot detergent, hot tap water, and final rinsing is done with the distilled water. Many containers have restricted openings, hence it is essential that the treatments in any washer we introduce through tubes into each container with a smooth flow out. All parts of the machine coming in contact with the treatments must be non-corrosive so that metallic contaminants from the machine are not deposited on the glassware. When high processing rates are not needed, a cabinet type washer may be used. In this machine, the ware to be washed is held on a rack within a cabinet while the machine automatically goes through the sequence of treatments of the cycle. Detergent treatment is usually eliminated in cleaning of new glassware because there is a risk of detergent residue. Without this detergent treatment, the cycle is essentially a rinsing process. To loosen debris by rinsing, alternating hot and cold treatments should be used. Final rinsing is done with filtered water for injection. The containers are inverted on spindles in the front of the machine and carried through a series of rinses in one rotation. For ampoules or containers with a markedly constricted openings that makes water drainage incomplete, the final treatment is usually a blast of clean air to blow out remaining water. After cleaning it, it is essential to protect containers from dust and other particulates that might be present in the environment. Hence, the clean containers are often removed from the rinser and placed in clean stainless steel boxes for sterilization under the protection of highly efficient particulate air filtered laminar airflow. Conveyor type rinsers have relatively high production rates. They have an advantage that they can deliver the clean container at the opposite end from that at which the unrinsed containers are loaded. The delivery end can therefore be in an adjoining room away from the dust and dirt associated with packing cartons. To eliminate the tedious handling of each individual container, rack loading rinsers have been designed with rack sizes adapted to container packing cartons. Minute quantities of oils, proteinaceous materials or other debris retained in the rinser from a previously used container could be carried through many rinsing operations and be deposited on glassware subsequently being processed. High-speed processing lines often are designed to clean containers by rinsing with clean water or sometimes simply with clean air under high pressure. The containers are shipped from the manufacturer on a support tray and closed within a shrunken, tightly fitted polyethylene sheet to minimize the accumulation of dirt during shipment. The cleaned containers are usually then fed by conveyor to hot air sterilizing tunnels, thereby minimizing handling of the container increasing speed of processing and allowing the clean sterile containers to be delivered through the wall into the aseptic filling room. The vials are cleaned by soaking them in detergent solution overnight to remove any sticking particles, grease, etc. and washed with tap water 3 to 4 times till soap solution is completely removed. Surface alkalinity is removed using 1% HCl and washed again with tap water. Rinsing is done with deionized water and finally with distilled water and subjected to sterilization for 4 hours at 200 degrees centigrade. Now we'll talk about the cleaning of closures and plastic components. Rubber closures are generally washed in a tank of hot detergent solution, that is usually 0.5% sodium pyrophosphate, by mechanical agitation followed by a series of thorough water rinsing, and the final rinsing is done with water for injection. The purpose behind this is to remove surface debris accumulated from the molding operation and from handling and leachable constituents at or near the surface. Part of the debris is attracted and held on the surface by electrostatic forces. Similarly, plastic materials accumulate surface debris. Abrasion may be occurring during agitation, resulting in small, loose pieces of the rubber or plastic material. This problem is more acute with two-component closures, like rubber disc inserted in an aluminum cap, because agitation usually causes more abrasion of the aluminum and produces small aluminum fragments, which adhere to the rubber disc or wedge between the disc and the cap. Therefore, the multiple objectives for washing closures and other parts include loosening debris, minimizing abrasion, and sweeping away the loosened debris. Sometimes household clothes washers of the horizontal rotating basket type or the center post agitator type have been used, but neither meets the requirements for an ideal washer for closures. More commonly today, the closures are subjected to gentle agitation with air bubbles, basket rotation accompanied by spray rinsing or simple water movement followed by extensive rinsing with water for injection. Handling after cleaning must be done carefully to prevent particle generation from abrasion and to prevent pickup of dust and other particulate matter from the environment. Therefore, the clean closures are often handled under the protection of HEPA-filtered laminar airflow. Sometimes the closures are subjected to an autoclave cycle as a part of the cleaning process. Such treatment aids in loosening surface debris and also leaches from the closure some of the extractives, thus reducing the subsequent contamination of the product. It should be remembered, however, that excessive heating is detrimental to the life of rubber as well as thermoplastic materials. Particular attention is needed in cleaning of rubber and plastic tubing. A special type of brushes may be helpful in reaching the lumen. The best and safe approach is to retain the tubing for reuse with the same product or discard after one use. Regardless of the type of cleaning machine, selected certain fundamental characteristics usually are required. Number 1, the liquid or air treatment must be introduced in such a manner that it will strike the bottom of the inside of the inverted container, spread in all directions, and smoothly flow down the wall and out the opening with a sweeping action. The pressure of the jet stream should be such that there is minimum splashing and turbulence inside. Direct introduction of the jet stream within the container with control of its flow is required. Number 2, the container must receive a concurrent outside rinse. Next one, the cycle of treatment should provide a planned sequence alternating hot and cool treatments. The final treatment should be an effective rinse with water for injection. Next one, all metal parts coming in contact with the containers and with the treatment should be constructed of stainless steel or some other non-corroding and non-contaminating material. Now we'll talk about the cycle of treatment. The cycle of treatments to be employed will vary with the condition of the containers to be cleaned. In general, loose debris can be removed by vigorous rinsing with water. Detergents rarely are used for new containers because of the risk of leaving detergent residues. However, a thermal shock sequence in the cycle usually is employed to aid by expansion and contraction, loosening of debris that may be adhering to the container wall. Sometimes only an air rinse is used for new containers, if only loose debris is present. In all instances, the final rinse, whether air or water for injection, must be ultra clean so that no particulate residues are left by the rinsing agent. Only new containers are preferred for penetrance. Now friends, we'll move towards next module, that is module 2, preparation of solution. Before going to the preparation of solution, we will try to understand what are the manufacturing requirements. The manufacturing of parental products occurs under aseptic conditions in an area that is only used for the preparation of sterile products. The large-scale manufacturing equipment within the facility must be capable of sterilization in situ. For example, the manufacturing vessels in which the solutions are mixed are generally jacketed and may be sealed. Temperature can then be applied to these to render them sterile. In addition, small-scale equipment which has been previously sterilized and sealed and raw materials including the therapeutic agent are entered into the aseptic manufacturing area through a special portal that is having positive airflow to prevent the access of microorganisms. The air supplied to the manufacturing area is filtered. Operators within the manufacturing area must wear specific, that is sterile, work clothes to ensure no operator contamination of the product as well as environment. The manufacturing of parental formulations is similar to that of non-sterile formulations, but the main difference is that parental products are rendered sterile. Now friends, we will talk about preparation of solutions that may be formulated as aqueous solutions or oily solutions. We start with aqueous parental solutions. The easiest and most suitable form of injectable preparation is an isotonic aqueous solution having pH near to that of blood and body tissues. The pH is 7.4. Buffer addition in the formulation may be necessary to stabilize the injection at an appropriate pH. If the medicament is prone to oxidation, then antioxidants may be included for stabilization of the product. Although in numerous parental routes, antioxidants are not permitted owing to their toxic or irritant characteristics. Many antioxidants cause irritation to mucous membranes and to the eye. Injectable solutions are usually given in single dose or multiple dose containers. Multiple dose containers, they are generally glass vials with rubber stoppers well suited for multiple withdrawals. Infusion fluids are aqueous solutions that are offered as large volumes than those normally administered by IV injection. Injectables ranging from 50 ml to 1 liter are usually given in polyvinyl chloride infusion bags. As the dose of LBPs is generally large, so any additives included in the preparation could have significant impact on the patient. Hence, only those additives are preferred for the preparations which are very essential for the stability of preparation, effective and not harmful to the patient. Additives like chelating agents, antioxidants, buffers, preservatives, etc., which are usually included to small volume parentals are hardly ever added to the large volume parentals. Even if these ingredients are required, must be included in minimum concentrations. Generally, large volume parentals should be isotonic. The main steps involved in the manufacturing of aqueous parental solutions are: number 1, the formulation ingredients including the therapeutic agent are dissolved in the main mixing vessels within the manufacturing chute. Next one is, if the nature of active ingredient is thermostable, the formulation is filled into the final containers and then sealed. Sterilization is then performed using moist heat sterilization. Unless the preparation is a multiple dose product, the inclusion of a preservative is unnecessary. If the nature of active ingredient is thermolabile, the product is sterilized using filtration and collected into a second mixing vessel from which filling into the final container is done. In some cases, it may be possible to fill the product into the final container immediately after filtration. Next one is oil-based parenteral solutions. These oils are preferred where drugs possess very low water solubility. Oily solutions are primarily intended for intramuscular administration and under normal circumstances should not be administered by other routes. The vehicle used varies widely from vegetable oils like arachis oil, sesame oils to simple esters like ethyl oleum. Moist heat sterilization cannot be used to sterilize oil-based solutions and therefore in the manufacturing procedure this limitation has to be considered. The main steps that are involved in the manufacturing of oil-based parenteral solutions are: sterilization of the oil-based vehicle containing the various soluble excipients within the mixing vessels in the aseptic manufacturing chute, performed using dry heat sterilization. If the therapeutic agent is stable under the conditions of dry heat sterilization, the drug may be incorporated or dissolved at this stage. This product is then ready for filling into the final container, which is then sealed. Alternatively, the product may be manufactured and terminally sterilized using dry heat sterilization. If the therapeutic agent is not stable under the above sterilization conditions, sterile drug should be dissolved in the sterile oil-based vehicle using normal mixing facilities. This product is then ready for filling into the final container, which is subsequently sealed. Now friends, we'll move towards next module, that is module 3, preparation of suspension. Suspensions, these are thermodynamically unstable heterogeneous systems containing dispersed solid phase and a liquid phase which may either aqueous or non-aqueous. Parenteral suspension should be sterile, free from pyrogen. It should be stable, easily suspendable, syringeable, isotonic and non-irritating. These characteristics make formulation of suspension difficult, usually in terms of stability, manufacturing and application. This suspension may be formulated as a ready-to-use injection or reconstituted preparation. Injectable suspensions generally contain 0.5 to 5% solids and having particle size less than 5 micrometer for intramuscular or subcutaneous administration. The specific problems associated with suspensions are viscosity, rheology, suspendibility, cake formation, crystal formation, syringeability, and particle size distribution. These need to be regularly monitored as a part of stability studies. Commonly employed excipients in the formulation of parenteral suspensions are antioxidants, wetting agents, solvents, preservatives, suspending agents, chelating agents, and tonicity modifiers. Approaches that are commonly employed to prepare a suspension include controlled flocculation, structured vehicle, combination of both. Basically, the choice depends on whether the particles in a suspension are to be remain flocculated or deflocculated. The controlled flocculation utilizes flocculating agent to form loosely bound aggregates or flocks that gets redispersed easily upon agitation. A structured vehicle approach utilizes suspending agent or thickening agent to keep the dispersed particle in a deflocculated state. The particle size distribution is very critical in suspension to make sure that the particles passes readily through a hypodermic needle during administration. A thixotropic behavior is desired for the suspension. Now we'll talk about aqueous parenteral suspensions. Drugs that are insoluble can be formulated as aqueous suspension. Suspensions are usually administered by intramuscular or subcutaneous routes and not as administered by the IV, intraspinal, intracardiac, intraarterial or ophthalmic routes. The factors affecting the drug release from the suspension and absorption from the intramuscular or subcutaneous injection site must be considered for the development of suspension. The properties of drug that are very essential for suspension formulation includes particle size and size distribution, pKa, water solubility, lipid solubility, partition coefficient, crystalline or amorphous nature of the drug. As suspension contains drugs that has been dispersed in the chosen vehicle, filtration cannot be performed to render the product sterile. Therefore, a sterile drug must be added to the chosen vehicle and suitably dispersed under aseptic conditions. Usually, the main steps involved in the manufacturing of aqueous parenteral suspensions are dissolution of the formulation excipients in an aqueous or hydroalcoholic vehicle within the main vessel, sterilization of the vehicle by filtration and collection into a second vehicle under aseptic conditions, dispersal of the therapeutic agent into the sterile vehicle. If required, the particle size of the dispersed phase may be reduced. The formulation may then be filled into the final container, followed by sealing. Next one is drug suspension are often physically unstable if exposed to moist heat sterilization. However, if the suspension is stable under these conditions, then the formulation may be manufactured and filled into the final container, followed by terminal sterilization. Next one is oil-based parenteral suspensions. Suspension can be prepared with oily vehicle also, but these preparations are not very common as compared to aqueous suspensions. These preparations can offer slow release or depot mechanisms by the deep intramuscular route. The manufacture of oil-based suspension combines the manufacturing considerations of both oil-based solutions and aqueous suspensions and includes sterilization of the oil-based vehicle containing the various soluble excipients within the mixing vessel and the aseptic manufacturing chute, performed using dry heat sterilization. Next one is mixing of the sterile therapeutic agent into the sterile vehicle prior to filling into and sealing the final container. If the formulation can physically and chemically withstand the conditions for dry heat sterilization, the product may be manufactured and filled in the final container. This may then be sterilized using dry heat. Before moving towards our next module, friends, I would like to suggest you please visit our website www.cec.nic.in for further reading and learning and more topics associated with your B.Pharm syllabus. Here you will find many lectures, e-contents, FAQs and many more. Hope this site will be a catalyst of learning for you. Now next module, that is module 4, filling procedures. We'll start with filling procedures for liquid. A liquid may be subdivided from a bulk container to individual dose containers very easily and uniformly as compared to solid. Mechanical subdivision of a mobile, low-density liquid can be achieved with light-duty machinery, but viscous, sticky or high-density liquids require specific machines to withstand the pressure. Now we'll start with filling procedure of liquids. Liquids, the certain fundamental features are found on all machines used for filling containers with liquids. A means is provided for repetitively forcing a measured volume of the liquid through the orifice of a delivery tube designed to enter the constricting opening of a container. The size of the delivery tube is governed by the opening in the container to be used, the viscosity and density of the liquid and the speed of delivery desired. The tube must freely enter the neck of the container and deliver the liquid deep enough to permit air to escape without sweeping the entering liquid into the neck or out of the container. To reduce the resistance to the flow of the liquid, the tube should have the maximum possible diameter. The delivery of relatively small volumes of liquids is usually obtained from the stroke of the plunger of a syringe. The stroke of the syringe forces the liquid through a two-way valve that provides for an alternate filling of the syringe from a reservoir and delivery to a container. For heavy, viscous liquids, a sliding piston valve provides more positive action. Filling machines must be designed so that the parts through which the liquid flows can be easily demounted for cleaning and for sterilization. These parts should also be constructed of non-reactive materials like borosilicate glass or stainless steel. Syringes are generally made of stainless steel when the pressures needed for delivery of viscous liquids or large volumes would be unsafe for glass syringes. Sterile solutions of relatively low potency dispensed in large volume and do not normally require the precision of filling that is needed for potent small volume injectables. Normally, bottles of solutions are usually filled by gravity, pressure or vacuum filling devices. Now we'll talk one by one. First is gravity filling. It is relatively slow but can be accomplished simply. The liquid reservoir is positioned above the filling line with a hose connection from the reservoir to a shut-off device at the filling line. The shut-off device is usually hand-operated and the bottles are filled to graduations on the bottles. Next one is pressure filling. It is operated semi-automatically and different from the gravity filling as in this liquid is under pressure. It is generally equipped with an overflow tube connected to a receiver to prevent excess filling of the container. Next one is vacuum filling. It is very commonly used in faster filling lines for large liquid volumes because it is more adaptable to automation. A vacuum is produced in a bottle when a nozzle gasket makes a seal against the lip of the bottle to be filled. The vacuum draws the liquid from a reservoir through the delivery tube into the bottle. Emulsions and suspensions often require specially designed filling equipment because of their high viscosity. To obtain a reasonable flow rate, high pressures must be applied or containers with large openings must be used to permit the entry of large delivery tubes. Sometimes jacketed reservoir tanks can be used to raise the temperature of the product and thereby lower its viscosity. It is normally necessary to keep suspensions and sometimes emulsions constantly agitated in the reservoir during filling so that the product remains homogeneous. And each subdivided unit contains the required amount of drugs. Now we'll talk about the filling of solids. Solids should be preferably free-flowing, uniform particle size and no electrostatic charge within mass of dry solid particles, free from clumping of particles and no formation of air pockets. One of the methods employs an auger in the stem of funnel-shaped hopper. The size and rotation of the auger can be adjusted to deliver a regulated volume or weight of material from funnel system into the container. Sterile solids like antibiotics are more difficult to subdivide accurately and precisely into individual dose containers than are liquids. The rate of flow of solid material tends to be slow and irregular, particularly if finely powdered, small granular particles flow most evenly. Containers with a relatively large opening must be used. Even so, the filling rate is slow and the risk of spillage is ever present. For these reasons, the tolerances permitted for the content of such containers must be relatively large. Sterile solids can be subdivided into containers by individual weighing. The operators can use a scoop that holds a volume approximately equal to the weight required, but the quantity filled into the container is finally weighed on a balance. When the solid is obtainable in a relatively free-flowing form, machine methods of filling may be employed. The major problems with these machines are stratification of particles due to varying particle sizes, the development of electrostatic charge within the mass of dry solid particles, the formation of air pockets, and even flow due to the clumping of the particles. These all cause uneven filling of the container. If uniform particle size of the solid is achieved and a small electric current is used to neutralize the developing charge, the problems can be minimized. One type of machine for delivering measured quantities of free-flowing material employs an auger in the stem of the funnel-shaped hopper. The size and rotation of the auger can be adjusted to deliver a regulated volume of granular material from the funnel stem into the container. In another type of filling machine, an adjustable cavity in the rim of the filling wheel is filled by vacuum as the wheel passes under the hopper. The contents are held by vacuum until the cavity is inverted over the container. When a jet of sterile air discharges the dry solids, this machine dispenses dry solids that flow less freely than those of other machines. Now friends, we move towards next module, that is module 5, sealing of the containers and closures. Sealing. Containers should be sealed in the aseptic area immediately adjacent to the filling machine. A sterile container, once opened, can no longer be considered to be sterile. Therefore, tamper-proof sealing is essential. Now we'll talk about sealing of ampoules, how ampoules are sealed. Filled containers should be sealed as soon as possible to prevent the contents from being contaminated by the environment. Ampoules are usually sealed by melting a portion of the glass neck. Two types of seals are employed normally. Number one is tip seals, that is also known as bead seals, and next one is pull seals. We'll discuss one by one. First one is tip seals. Tip seals are made by melting enough glass at the tip of the neck of an ampoule to form a bead and close the opening. These can be made rapidly in a high temperature gas oxygen flame. To produce a uniform bead, the ampoule neck must be heated evenly on all sides, such as by burners on opposite sides of stationary ampoules or by rotating the ampoule in a single flame. Care must be taken to adjust the flame temperature and the interval of heating properly to completely close the opening with a bead of glass. Excessive heating will result in the expansion of the gases within the ampoule against the soft bead seal and cause a bubble to form. If it bursts, the ampoule is no longer sealed. If it does not, the wall of the bubble will be thin and fragile. Insufficient heating will leave an open capillary through the center of the bead. Now next one is pull seals. Pull seals are made by heating the neck of the ampoule below the tip, leaving enough of the tip for grasping with forceps or other mechanical devices. The ampoule is rotated in the flame from a single burner. When the glass has softened, the tip is grasped firmly and pulled quickly away from the body of the ampoule, which continues to rotate. The small capillary tube thus formed is twisted closed. Pull sealing is slower, but the seals are more sure than the tip sealing. Powder ampoules or other types having a wide opening must be sealed by pull sealing. Fracture of the neck of the ampoules during sealing may occur if wetting of the necks occurred at the time of filling. Also, wet necks increase the frequency of bubble formation and unsightly carbon deposits if the product is organic. Before and after filling of solution into ampoules, purging of inert gas such as nitrogen or carbon dioxide may be performed to displace the air in the head spaces to prevent oxidative degradation of sensitive drugs. Ampoules are closed by melting a portion of the glass of the neck to form either bead seals or pull seals. Wet glass at the neck increases the frequency of bubble formation and unsightly appearance and contaminated deposits of carbon as a result of the effect of heat of sealing on the droplets of product. Excessive heating of air and gases in the neck causes expansion against the soft glasses with the formation of fragile bubbles at the end point of seal. When ampoules are used for lyophilization, they must be filled and loaded into lyophilization chamber unsealed. When lyophilization is complete, they must be removed from the chamber and transported back to the filling line for sealing. Now we'll talk about the sealing of vials, bottles and cartridges. Rubber closures must fit the opening of the container snugly enough to produce a seal. It may be inserted by hand using forceps. When closures are to be inserted by machines, the surface of closure is usually halogenated or coated with silicone to reduce friction. Aluminum caps are used to hold rubber closures in place. Single caps may have a permanent center hole or a center that is torn away at the time of use to expose the rubber closure. Double aluminum caps usually have an inner cap with a permanent center hole which in use is exposed when the entire outer cap is torn off. The triple aluminum caps are used for large bottles with rubber closures having permanent holes for attachment to administration sets. The inner cap with a permanent center hole remains in place during use to secure the rubber closure. The thin disc is used in conjunction with a thin rubber disc to seal the holes through the closure. The outer cap holds the disc in place and is torn away at the time of use. Single aluminum caps may be applied by hand crimping devices, but double or triple caps or large production lots require the use of heavy-duty motorized crimping machines. Now friends, it's time to summarize our episode. Sterile products preparations constitute a series of events. Each step in the process must be controlled very carefully so that the product will have its required quality. Each process must be validated to ensure the quality of product. Cleaning of containers and closures must be done meticulously. Even unused, new containers may also be contaminated, hence they must be cleaned thoroughly to avoid the risk of contamination. The manufacture of parenteral products occurs under aseptic conditions in an area that is only used for the preparation of sterile products. Solutions are most commonly used injectable preparations. This solution must be an isotonic aqueous solution with pH equivalent to blood. Injectable solutions can be presented in single dose as well as multiple dose containers. Sometimes oily solutions are preferred where drugs possess very low water solubility. Mainly these oily solutions are intended for intramuscular administration. Parenteral suspension is another difficult dosage form to formulate. It necessitates balancing of variable so that it can be easily resuspended and passed through syringe. The particle size distribution is very critical in suspension to make sure that the particles pass readily through a hypodermic needle during administration. During the product filling, the most stringent requirements must be exercised to avoid contamination, especially if the product has been sterilized by filtration and will not be terminally sterilized. Liquids are usually filled by gravity, pressure or vacuum filling devices. Containers should be sealed in the aseptic area immediately adjacent to the filling machine. A sterile container once opened can no longer be considered to be sterile. Therefore, tamper-proof sealing is essential. In summary, this module will help students to understand about cleaning of containers and closures, preparation of solutions, preparation of suspension, filling procedures for solids and liquids, sealing of ampoules, vials, bottles, etc. So friends, thank you for this time.